Alright, it's time to get started. Big announcement today. There's an event. There is a data science club. There's a workshop. They have an event. It's organized by the data science club. If none of this is interesting to you, there's free pizza. It's at 4:30. You should check it out. If you want more information, go to this URL, datascience.utah.edu/club.html. Could be fun. And there will be more such events going ahead. I think this week it's Qualtrics. I think to discuss any concern. Any questions about the logistics of this process? About the exam or the homework?
How long should the exam take?
Sorry?
How long do you expect it to take?
For me?
For the slowest person in class.
I don't know. I mean, so in the past, examples, if you have enough number of examples of that's less than m, then the learning algorithm can learn, where we define learn as having a classifier with low error. So the learning algorithm can learn any function in f for any distribution over the examples, and it can do so. It can do that with high probability. Yes.
Sorry, but m is polynomial with respect to what variable?
M is polynomial in 1 over epsilon, 1 over delta, the size of the hypothesis class, and the dimensionality.
Okay.
N is the dimensionality of the features of the feature space. So one thing to keep in mind is this definition is a mouthful. I mean, I don't have to tell you that, you can look at it. But it is just a definition. All I'm saying is a concept class is called pack learnable. I'm just attaching a tag to a class of functions if these properties hold. I'm not telling you that anything more. All I'm saying is this is what a pack learnable concept class is called. I could have defined an empty set. Maybe there are no no concept classes that are pack learnable. But no, actually I've already proved to you that there is at least one concept class that's pack learnable. In the previous few lectures, we discussed these conjunctions, and conjunctions had this property. If you had these many examples, then with high probability you will get a classifier that has no error. So at least one class of functions is pack learnable, so this is not a trivial definition. This is, by trivial I mean this is not naming an empty set. So, and this is capturing the intuition that A, we have to live with some error, epsilon, small error, but maybe non-zero. We have to live with some error, and it's possible that we just get so unlucky that our entire training set is not representative of the data, of the true concept. In such a situation, our classifier, our learning algorithm will not produce a good classifier, and that is going to have a probability less than delta. So such situations are so rare that we are willing to admit that we have to live with that. Questions? Yes?
So it might so happen that H has some continuous parameters, in which case the size of H would be...
That's a very good, yes.
So can we still talk about polynomial in size of H when size of H is...
So let me repeat the question. That's a good observation. This quantity here, size of H, could be infinite. If you have let's say H is the set of all linear classifiers. How many linear classifiers are there? Infinite. And polynomial in an infinite thing is meaningless. So when we come to, so currently there is as far as this definition is concerned, there is another unstated assumption that the size of H is finite. So Boolean functions, for example, we have finite concept classes. We will drop that assumption once we come to the discussion on scattering, where we'll see that even for infinite hypothesis classes, we can associate an idea, this dimensionality called the VC dimension, which serves as the size of H in this theory. But we'll deal with that maybe in 3 weeks.
Another question is that when we talked about H and concept class last lecture, you described H as being a superset of the concept class. And I would have reversed that, because I thought part of the point of the hypothesis class is that, or space, is that we wanted to reduce the number of functions we had to search over by bringing knowledge to the table.
So let me just repeat that question for if you didn't hear it. In the last lecture, I mentioned that we want to think of, so let's say we have a concept class C, and we have a hypothesis that is H. In the last lecture I mentioned, or maybe I shouldn't have drawn this so big, maybe I'll just redo this. You have a concept class C and a hypothesis space H. And the idea was, you pick any concept class, any function inside C, and it's going to be in H. That's true here. This is the only situation that we can hope if we had a consistent classifier, if we are hoping for a consistent classifier. But the question was, this seems to counter this intuition that we need to reduce the search space. Here we have increased the search space from C. We wanted to start, in the first or maybe the second lecture I mentioned learning is pointless if we are going to search over extremely large spaces. We need to reduce the search space. And what is what's happening? What's happening is, there's another set of functions, the set of all possible Boolean functions, which is much, much bigger. Let's call this B. B is the set of all Boolean functions, and the size of B is you have n features. How many Boolean functions do you have? So you have a lot of functions. The assumption is that the concept class is really small inside that. We never have access to the concept class for real. We never actually know what is the concept class because it's part of this unknown. The only thing that we care about, or the only thing that we can control, is a hypothesis class. And we always have to reduce the hypothesis class compared to a set of all possible functions. The theory that we are building is now asking, yeah, sure, we have reduced the hypothesis space, but maybe there's another class of functions, the concept class, which may be contained in the hypothesis space, which may be outside the hypothesis space, let's call this C prime, or it may have an overlap with the hypothesis space, C double prime. We don't have access to this, but we are imagining the situation and asking what happens in each of these cases. And really the two interesting cases are C is completely contained inside H, or C has some overlap with H or maybe outside. In either of these cases, we want to prove learnability theorems which covers all possible cases. So the cases are C is completely contained inside H, or C is not completely, C has some functions that are not inside H, at least some functions. So that covers both these cases. Case 1 and these two together, case 2. But still we have reduced the hypothesis space. We are just considering two possibilities for the true function could have been inside H or maybe not. Currently we are considering the case 1 here, the true function is inside. Once we move to agnostic learning, we'll consider the other thing. Yeah.
Why do we, I'm not sure I'm going to explain this properly, but why do we talk about the entire concept class C as opposed to just talking about the true function? Why do we say C is inside H rather than saying true function is inside H?
Because, oh yeah, sure. For most of the time that won't matter actually. Yeah, I see your point. We really care about this one function which is an unknown. Why are we now inventing a set of functions that are unknowns? The reason we want to do that is to make statements of the following kind. Suppose the true function was a Boolean. Suppose the true function was a monotone conjunction. And I'm trying to approximate that function using a linear classifier. How could I learn? All I know is it's a monotone conjunction. I don't know which one. So can I approximate one class of functions using another class of functions? We want to make statements of that kind, rather than a function.
Okay.
Alright, so that was pack learnability. We saw that. Do you have a question?
What if the size of H is like 2 to the n?
2 to the n is actually okay.
But it wants to be polynomial with H, but it can be polynomial in n.
Right, so yeah, so eventually what will happen is, we'll get to that in a minute. Yeah, there's some redundancy in this definition that will get resolved very soon. Yes. So that is just pack learnability. I've just defined this. I have said nothing about the algorithmic complexity of learning. There's also this idea of efficiently pack learnable. Efficiently pack learnable is, a concept class is said to be efficiently pack learnable if the function, the concept class is pack learnable, so all of this definition, and 2, the algorithm finishes running in a polynomial time. there's a, the algorithm can actually learn in a reasonable time.
Would you also say polynomial space?
I have not seen too much of that because most learning algorithms tend to be rather efficient.
Maybe polynomial time implies that.
I think, yeah, so yes, yeah. The efficiency includes space also, but you don't see that a lot. There's a very inefficient learning algorithm that is consistent, which is remembering every training exam space-wise. You can't, it's inefficient, but it turns out that's a very popular learning algorithm in two ways. The simplest version of that is called a database. You just remember all examples. There's also k nearest neighbors. Nearest neighbors, which we'll come to much later in the semester. The learning part of it is essentially just remembering examples, and that requires a heavy amount of space. But from the computational point of view, the most important concept one important concept that you have to kind of internalize is this idea of a sample complexity. The sample complexity is an information theoretic requirement. What it says is there enough data in only m examples to sufficiently convey the concept to the learner, to any learner? So sample complexity for a concept class is how many examples do I need so that learning can succeed. That's that m there. And then there's, of course, we need polynomial time complexity because we are, computer scientists, and so we want efficient algorithms. For pack learnability, these are like minor points. The only other thing I wanted to remind you is it's a worst case definition. It's a worst case definition in the sense that these requirements should be met independent of what the actual distribution of examples is. It should be met for every distribution, which means the learning algorithm can't internally say that, I'll work for this particular distribution of examples, but not something else, because then it's not a worst case definition. It should also work for every function in the concept class, which means that the learning algorithm can't say, you have the class of set of all these functions that could possibly be the true function. If the true function was either this f1 or f2 or f3, I'll be able to find it, but nothing else. That's not a packed learning algorithm because it's not working for every target function. Questions while I switch slides?
So that's why, part of the reason why we need H to be a superset of C too.
For exactly that.
Okay.
Yes. Alright, so now I'm going to introduce something fun. Oh yes, sorry.
Excuse me, so for the worst case, the accuracy needs to be met both for the all the concept class and all the distribution, or for one distribution and one.
For the worst, for every distribution, for every function.
What's the difference between the pack learnable and the worst case?
No, this is pack learnable. Pack learnable is the worst case. It considers the worst case situation. It considers the worst case situation in the sense of it completely ignores the distribution. It does not make any assumptions about the distribution. It does not make any assumptions about the true function, other than the fact that the true function belongs to the concept class. Alright, so now let's talk about this idea about Occam's razor. Just to remind you where we are, we analyzed this class of functions for the conjunction class, and we proved some statement that said if you have m examples and this m is more than some number, that number is polynomial in all these interesting parameters, then with high probability you can produce a classifier that has low error. The goal now is, can we take that kind of analysis and generalize that to arbitrary classes of functions? I don't know what the class of functions is. Let's just see if we can generalize this to all classes of functions without making assumptions about. So if you remember the conjunction proof that we saw, made these rather tedious arguments about this variable being bad and that variable being bad, and can we get around such arguments and talk about function classes without making assumptions about their nature? So, again, I like starting topics off with history. Occam's razor is one of the oldest philosophical concepts that have been independently rediscovered in pretty much every school of philosophy. It's named after this character called William, and the Latin statement is actually pretty cool. It says, never posit plurality without necessity. I'm not sure that's a valid translation. What it means is that if you have two explanations for some data, one of them is simpler and the other one is more complex, prefer the simpler explanation. There should be a general bias towards simplicity because complexity could lead to overfitting, essentially, if you're using language from machine learning. What we'll do now is we'll prove a theorem that actually says the same thing. It's called the Occam's razor theorem. In order to prove this, we're going to first prove the following claim. Suppose, and I'm not setting up the whole thing, I'm not setting up all the symbols here. These are the symbols that you're all familiar with. So, let's say we have a data set with m examples. Okay? And we have some learning algorithm. We don't care what the learning algorithm is today. And let's say this learning algorithm produces a hypothesis H that is consistent with all m training examples. Then I'm going to prove to you that the probability that there is some hypothesis inside the hypothesis class, I don't know which one, there's some hypothesis inside the hypothesis class that is both consistent with the entire training set and has a generalization error that's high, that's more than epsilon. You have the probability that there's a function that's consistent with the training set and has a high generalization error is less than this quantity, size of h times 1 minus epsilon power n. Before we go into the proof of this, there's a statement, I want you to kind of let the statement sink in. Any questions about this? Okay, maybe I'll go ahead to the proof and you can think of questions along the way. Oh, so in this analysis, what I'm going to show you is Occam's razor assuming this idea of consistency. Consistency meaning the classifier is consistent with the entire training set. So what this statement is really talking about is the probability that there's some hypothesis H that is consistent with the training set and yet bad is low. And it keeps getting lower and lower as m increases. Because m is in the exponent of a number, so you have size of h times 1 minus epsilon power m. And this quantity is less than 1. Which means as m gets higher, the whole thing keeps decreasing. So as you see more and more training examples, you will, the probability that you have a hypothesis that is consistent with all the training examples and yet has high generalization error is going to get low. In order to prove this, let's say that we have this one hypothesis. We have some bad hypothesis that has a high error greater than epsilon. What's the definition of, can someone tell me what is error, the true error of a hypothesis? What's it defined to be?
Probability when x is part of b such that hx is not equal to fx.
The probability
X is part of h such that
x is drawn from the true distribution.
yeah, true distribution such that fx is not equal to hx.
Okay, yes, that's right. So f of x not equal to. So this is the true error. So let's say we have a hypothesis that has a high probability of this event happening. What does that mean? It means that you pick an example, the probability is that this function h is consistent, meaning this is not true, this event is not true, is 1 minus the error. Right? So the probability that h is consistent with one example is simply the probability that f of x equals h of x for some example, which is less than 1 minus epsilon. Right? This one example came from the training set. Remember that the training set is drawn from the same distribution. This one example is in the training set. But the training set consists of m examples. Each of them is drawn independently, which means the probability that h, this function h that is bad, is consistent with our entire training set is this quantity power m. It's less than that quantity power m, because each of them is drawn independently. You have m independent trials of this event happening, because we've already assumed that the function is consistent with m examples. You have m independent trials where the function is consistent with that with each example. The probability that h is consistent with all examples is less than 1 minus epsilon power m. Okay? The probability that there exists one such function is simply the number of functions that we have times this quantity. Is less than that. Is less than the size of h times 1 minus epsilon power m. How did we get there? The union bound. Going from here to here is just the union bound. This is simply asking probability, the line on top is probability that this particular h is consistent. And this line is probability there exists h in h such that so going from here to here requires the union bound, because there can be only m such examples. Sorry, a size of h such functions. Any questions before we move on? This, by the way, proves the claim. The probability that there's a hypothesis that is consistent with m examples and is yet known to be a bad hypothesis is less than the size of h times 1 minus epsilon power m. If there are no questions, I'm going to move ahead. Yes?
So intuitively, this is saying if we fit all of our examples, it's really unlikely that we found a super bad hypothesis because we still fit all our training examples.
That's exactly right. That's exactly right. And that's really all that is. If we, can you repeat that a little louder, because that was a good summary.
Sure. So we're saying here that if we fit all our training examples, it's really unlikely that we found some terrible hypothesis because we fit all our training examples. So we know we at least fit that many.
Exactly. Yes? Can you speak up?
If n is say polynomial in terms of the other ones, then is this exponentially unlikely because we're something less than 1 to the n?
Yeah?
Okay.
Yes. Okay, so this is just an interesting lemma that will help us prove our eventual theorem, which is called Occam's razor. Now, I have, on one hand, as we said that, this probability, so probability of h, element of h consistent, is less than this quantity. All I've said is the probability that some hypothesis is consistent is less than this thing. But we still don't know if the quantity in the circle is small or not. Maybe the quantity inside the circle is huge. Maybe life is not that good after all. What we would like is that the size of h times 1 minus epsilon power m should be small. In fact, let's make it really small. Let's make it smaller than some delta that we control. We want to make it less than delta. We want size of h times 1. By the way, quick show of hands. Is this tiny font visible in the last row? Okay, because I wouldn't be able to see it. So we want the size of h times 1 minus epsilon power m to be less than delta, because if that is true, then this quantity, then this is also going to be less than epsilon. The probability, because we know that, is going to be less than delta. We know that the probability that a hypothesis is consistent and has high generalization error is less than the size of h times 1 minus epsilon power m. If we bound it on top by delta, then life is good. At this point, it's just algebra. From now on, there's nothing more complicated to do. I take log on both sides, and really what I want is an expression that involves m on one side and everything else on the other. We could have done, just move done the simple thing and literally just move m on one side, but we can even get a looser bound, or a safer delta by kind of loosening this bound using the same thing that we saw before written in a different way. We know that e power minus x is greater than 1 minus x. We're going to apply the same thing again, do a little bit of rearrangement to this quantity here, and we'll get an expression that looks like this. So quick show of hands, how many people would like me to work this out, and how many people can do it yourself? Option 1, how would you? Option 1 is, how many of you would like me to work this out? Okay, at least one person does it, so let's do it. So we want the size of h times 1 minus epsilon power m to be less than delta. We would like that to be true. And I'm going to do a slightly different analysis here, which is equivalent but looks structurally different. We know that from here that 1 minus epsilon is less than e power minus epsilon. When I say we know that, I mean this is something that's easy to prove just using the properties of the function e power minus x. But this means 1 minus epsilon power m is less than e power minus m epsilon, just taken into the power m, which means the size of h times 1 minus epsilon power m is less than the size of h times e power minus m epsilon. Right? Okay. We want the left hand side to be less than delta. But let's be generous. Let's make the right hand side less than delta, which will automatically give us. So if the size of h times e power minus m epsilon is less than delta, then this is true. And if the line on top is true, then the probability of having consistent classifiers that are still making high generalization error is going to be less than delta. So if this is, let's see what happens if this is true. For this to be true, we can now take log. Log size of h minus m epsilon is less than log delta. And I'm going to move things around. I'm going to move m to that side and move the log delta here, so I get m epsilon is greater than log size of h minus log delta. But I can rewrite log the minus log delta as log 1 over delta. So this is, and I'll move the epsilon down. So I get m greater than 1 over epsilon times so far so good. Now, if this is true, so if this statement that I put a star against is true, this is exactly the same as saying this thing. I just, from here to there is just algebra. I've just moved terms around. Which means if m is greater than this quantity, then the expression on top, this thing on top, is implied. Right? Which means if you have these many training examples, the previous statement follows. If you have these many examples, then this statement false. In other words, if you have those many examples, the probability of getting a bad hypothesis that is still consistent with your entire training set is small. So let's revisit this. This is essentially the Occam's razor theorem. I basically wrote the theorem. So let me collapse everything and state it formally. Let's say you have some hypothesis space H. Then with probability 1 minus delta, with high probability, a hypothesis that's consistent with an entire training set of size m will have an error, generalization error, less than epsilon if you have at least m examples, if m, the number of examples that you have is at least this quantity, is more than that quantity. If you have at least these many examples, then all you have to do is be consistent with that entire training set and life is good. So you already have a learning algorithm. The job of a learning algorithm is to discover a consistent classifier. All you need is to be consistent. And by the way, can someone shout out the name of a learning algorithm that always produces a consistent classifier if you have no noise? Decision trees. So if you have a decision tree learner, for example, and you have these many examples, life is good. Let's kind of tease this apart. What does this mean? If I want a low error, if I want error less, if I want the epsilon to be very, very small, then the sample complexity increases. M is the sample complexity here. How many examples do you need? If you want a low error, then you need more examples. So you need more examples to get a very close approximation. If you have a large hypothesis space, then learning becomes harder because you need more examples. Because log size of hypothesis shows up. Higher sample complexity if you have larger hypothesis spaces. If you want a high confidence that your learning algorithm is going to be that your classifier is going to have low error, or if you want to have high confidence on your learning algorithm, then you need more training examples. So, by the way, notice that this m is polynomial in 1 over epsilon, it's polynomial in 1 over delta, and in the size of the hypothesis space. This is a pack guarantee. This is a general version of a pack guarantee which actually gives you a recipe. Talk about that in a minute, but any questions about this? Yes?
I'm still confused on what delta is.
What delta is the following, okay? Suppose you have the following experiment. The event of interest is your procedure. Let's call it a learning algorithm, but it doesn't have to be a learning algorithm. It's some procedure produces a classifier that has low error, low generalization error. Right? There's an event. Your classifier can produce your learner can produce a classifier that has a high error or a low error less than epsilon. Now, I count something as success if the learner produces a classifier with low error. Delta, 1 minus delta, is the probability of success, defined that way. Or delta is the probability of failure. Probability that your learner has produced a classifier that does not have low error.
So, does that relate directly with the epsilon and the error?
It internally might depend, it clearly depends on the epsilon. So this expression relates m, epsilon, the type of h and delta clearly. But the way to think about it is what could drive your learner to produce a classifier that's consistent with your entire training set and yet has high error. That could happen if your training set itself was not representative of the future. Essentially, delta is asking in one version of this theory, delta is asking what is the probability that your training set is not representative. what is the probability that your learner has been fooled by a training set?
Well, isn't epsilon, so epsilon is so we have an H, a classifier.
Yes.
The error is
Epsilon.
epsilon, which is taken, we just test every example that
That exists in the, that can possibly ever exist. Even the ones that you see and the ones you do not have access to.
And so delta is the
Probability, go ahead, you say it in your own words.
So the delta is the probability that that's wrong, or
Delta is the probability that, so it's easier to think of 1 minus delta. 1 minus delta is the probability that a classifier with low error has been chosen. The uncertainty here could be because of the training set, because the training set has fooled your learner. The uncertainty could be because your learner itself has some stochasticity. We will not worry about that now because we are assuming consistency. But for now, the uncertainty is because your training set is surprisingly underrepresented. And delta is 1 minus delta is expressing your surprise. How unlikely would it be that your training set consisting of m examples has managed to fool your learner into thinking that this particular hypothesis is good? It is so unlikely. In fact, it is such an improbable event. It's an event with probability only delta. So it's essentially expressing this surprise over seeing underrepresentative training sets.
it just sounds like delta is the more interesting variable here.
Delta tends to be the variable that gives people some amount of grief mentally, thinking about it. Epsilon is but I would argue that epsilon is equally interesting. In fact, the thing that is of most interest is epsilon because we care about the error of the classifier. We want epsilon to be small. In fact, we want epsilon to be small and delta to be small. Right? But that's a good, think about it a bit more because if this is the first time you're seeing this, it tends to be a little bit wacky. Alright, let's think about this a bit more. This theorem is called the Occam's razor theorem because it imposes a preference for smaller hypothesis spaces. If you have larger hypothesis spaces, learning becomes hard. Effectively, it shows when an M consistent, this is just a word I made up, an M consistent hypothesis, a hypothesis that's consistent with M training example, generalizes well. And essentially what this theorem, the theorem says is, maybe it is quite likely, not quite likely, but it's entirely possible that a complicated explanation, a complicated hypothesis, is consistent with the entire training set. But simpler hypothesis spaces, are less likely to fool us by being consistent with many training examples. You've already seen an example of this when we spoke about decision trees. It is, if you allow your decision tree to grow arbitrarily deep, you will probably fit any training data if there's no noise in the data, right? Which means that it will even fit all these weird, actually, let's say even if there is noise in the data, it will fit the data set if the data set is internally, does not have two examples with different labels. It does not have the same example with two different labels. So your decision tree learner will always fit any training set, a Boolean discrete training set. What this means is that it will also fit the noise. Larger trees tend to be more, might have more error because they might just overfit the training set. What this says is, yeah, of course, it's always possible to find a complex explanation for your data, but it is unlikely that a simple explanation that perfectly explains your data is wrong, because how could it be that a simple explanation explains so many training examples and yet be wrong? By simple explanation, the simplicity of the explanation is defined by the size of the hypothesis space. smaller search spaces are better. So smaller decision trees that perfectly fit your training set are better than very, very large decision trees that also perfectly fit your training set. So it imposes a preference. Questions?
Well, I mean, it's only, so having a larger hypothesis space is only significant asymptotically, right? Because say it's twice as big, that still means also need twice as many samples?
Yes.
Okay.
Yes. So it's not twice, right? It's log. There's a log there. But
Oh, sorry, so it's, okay.
so larger hypothesis spaces demand more examples to learn. With this guarantee, I mean, you might be able to fit the training set, but if you want a guarantee, you will not get it. So already this gives us a general scheme for learning. Let's say you have a training set with, okay, there's clearly an error here. I'm not going to call it D, let's call this S. So let's say you have a training set that consists of M examples. All you have to do is find a hypothesis, let's say you have some function, hypothesis in this hypothesis space that's consistent with all M examples. If M is large enough, then the consistent hypothesis must be close enough to F. That's what this theory tells us. All you need to do, one more thing you need to check is that the size of H is not so large that M does not end up being exponential. So I can create a set of functions where log size of H is exponential in the dimensionality, for example. You need an exponentially many number of examples, so any set M of M examples, any set of M examples is not good enough unless you have exponentially many. So the general recipe here is, given a hypothesis space H and a training set M, you pick an epsilon and a delta, let's say, something that you are comfortable with. You are willing to live with this much error and you want this much confidence that you will find a good classifier. Using these three things that you have, M, H and epsilon, you can now ask how many examples do you need? You can plug this in, you can ask how many training examples do you need? If you have these many training examples, all you need to do is find a classifier that's consistent with the training examples. Right? Because then you get the pack guarantee. You need to do that, and you need to also show that such a function can be found efficiently. So this is the second bullet point here is about the efficient pack learnability. And we've actually worked through this exercise. We've worked through this exercise for the class of conjunctions. The elimination algorithm that we saw a few weeks ago finds a hypothesis that's consistent with the training set. And it turns out that we proved a pack guarantee for elimination also. So if you are somehow in this fortunate situation in the future where you know that the true function is always a Boolean conjunction, you can say proudly that you know how to learn it. With formal guarantees, you can come with a certificate that learning is possible. You can check how many examples are needed. So I'm going to, basically I'm almost done with this part. Are there any questions? About pack learning, not just about this slide, but about Occam's razor in general. Yes?
You said that the simple argument is valid for others as well because it has seen so many right examples. So it can't be wrong in future.
No, it's not that it can't be wrong. It's going to be it's going to be wrong only epsilon number, epsilon
but the thing which overfits our data, that has also seen that many examples. So by the same argument, it is wrong. I mean, it's not that correct. So, I mean,
it is not that. That's why this gets a little tricky. Let me try to paraphrase your question so that I understand it, and then try to answer it. Suppose you have two situations. Okay, you have one classifier that is small and fits m examples, and you have another classifier that is extremely large and fits m examples. Once this is done, I can't really say much. Both of them are consistent with the training set. Both of them enjoy the same guarantee that we had, except this large classifier was found in a large set of functions. So it is going to be easy to find a huge classifier. It's going to be easy to find a function if your search space is large that overfits the training set. It's going to be more difficult to find a function. When I say difficult, statistically, it is unlikely that a small function overfits the training set. Once you've found those functions, then it's a different question. The argument is not valid anymore. This is before. This is when you're choosing your hypothesis space. So I'll give you an example. Let's say we have a data set, some fixed training set, m examples. Now I want you to consider two classes of functions. Class A is the set of all decision trees that have a depth no more than 2. Class B is the set of all decision trees that have a depth no more than 100,000. Okay? So depth 2 and depth 100,000. Let's say you find a function in this set that fits the training set. And let's say you find a function in this set that also fits the training set. The question is, which of these would you prefer?
Yeah, but I mean that doesn't guarantee that it will be better in future. It could be, I mean, just accidental that the simple person is getting all of them.
Someone else is also.
But the distribution is same, right? So if the training, it did fit the training set, it should with high probability fit the test set as well because the distribution is same.
The distribution is the same except the probability that, so let's go back to this thing here. Let's go back to this statement. Yes, in both cases, the probability that there is some function of that kind that fits the entire training set is actually this statement here. Yeah. In both cases, the probability that there's some function of that kind that fits the hypothesis space, so that fits the training set, is less than this quantity. But let's say you have H1, I called it A, so I'll call it A again. A is decision trees, depth 2, and B depth, well, I don't know what I said, so I'm going to say million. Okay? Then the size of the hypothesis space, size of A, is much smaller than the size of B. Right? The probability that there's the consistent classifier, there is a consistent classifier which is consistent with the training set and has a low error is much, sorry, what did I say? The probability that there's a consistent classifier and has a high error is much lower here than here. Right?
A and B are both testing on the same set, right?
Testing is a word that's loaded, so can you use a different? A and B are, what do you mean testing?
So I get that A and B, like A is the size of depth 2 tree and B is the size of So, but their accuracy, if you know A has an accuracy of like 90% and B has an accuracy of 90%.
A is a set of functions.
You should choose A because it's of size depth 2, because it's simpler.
Essentially what this is saying is that it is more unlikely that a function here would be perfectly explaining the entire training set. It's more unlikely that a function here would explain the training set than it is that a function here explains the training set, because there are so many more functions here. You can always find a function. And that is why, if it is so unlikely, maybe you should prefer this, because it couldn't have happened by chance. You know, it couldn't have happened, it couldn't be a statistical anomaly. Alright, so this is an important concept. You have to go back, revisit this, kind of let this settle in, because if you've not seen this kind of this style of reasoning before, it can be a little troublesome. I want you to and just because this is not going to be covered in the exam, the midterm, does not mean it's not important. In fact, this is like if there is just one lesson that I want you to take from the entire machine learning class for the entire semester, it is the following. Prefer simpler classes of functions. Why? Because simpler classes of functions tend not to be fooled by training sets. If you have a simple class of functions and a complex class of functions, prefer the simple ones because they are often good enough. Yes?
Can you explain how it follows that having a small hypothesis space implies that you have simpler hypotheses?
That's not at all true. That's not at all true. In fact, that's a subtle question that I was hoping nobody would ask. A small hypothesis space does not necessarily mean simpler functions. The small hypothesis space only means small hypothesis space. Maybe I have a hypothesis space with 3 functions, and each one of them is a decision tree of length million, of depth million. 3 really complex functions, good functions, but still the search space is small. We define the complexity of the hypothesis space by their size. That's how we define it. If you're in general, we are thinking of make the search space small, and that's a general life lesson. If you want to search for an answer, first start off with simpler defined as in start off with smaller search spaces. All right, we should stop. Very quick exercise to kind of mull over this. Think about the size of decision trees. This may be a lot trickier than you might think about it initially, because there's also the question of ordering and such things. And then there are decision trees that are structurally different but actually have the same Boolean function. You guys have done that too. So how many decision trees are there that are functionally equivalent? Not structurally, but functionally equivalent. The way to think about that is how many Boolean functions are there and how many decision trees are there that are functionally equivalent. I'm not going to give you the answer. I want you to think about whether decision trees are efficiently packed learned, and you can come back to this after when we meet again. So what I'm going to do now is take a break and empty slides and open it up to questions. You have a midterm in the next lecture, so any questions about anything that we've seen so far, or homework? And I know there were a few questions, so I'll go in the order in which people approached me. You came to me before class, and then you had a question, and then you. I'll let you think.
Okay, there was a question on the homework, and also this question appeared in the slide deck for perceptron. So it relates to the Occam theorem and to the bound for the number of mistakes that perceptron algorithm can make. And I think the question said something about the number of mistakes that perceptron would make over a class of all disjunctions.
Okay.
And I was a little bit confused about even the meaning of that, because normally I think when we're looking at this theorem, we're looking at a series of examples that are positive and negative, and we're trying to find an R that contains all of them, and basically a margin that would separate them, given that they're linearly separate.
Right.
So when you say over like a class of functions like that, I'm not sure what the intended meaning is, because different functions would return different pluses and minuses in different locations.
Right. So let me.
Can you just explain maybe the concept a little more?
Yeah. So the question is, Novikov theorem talks about a particular function, hidden function that we are trying to learn. But maybe the discussion questions or the exercise questions I had after that was, how many mistakes would a perceptron make on the class of disjunctions, let's say? And the question is, it's not that we care about the class of disjunctions, we care about a function. And maybe changing the function would changing the function and the order in which they are presented would change the theorem, would change the mistake bound. Is that right?
Yes, possible.
So the answer there is, usually when these questions come up, the way to think about it is not in terms of a function, but in worst case. What is the worst number of, what's the worst possible function among this class of functions?
Okay, so I should think of the worst one and then try to construct a margin, for example.
Something like that. So let me give you an example for the class of disjunctions in 2 dimensions. Okay? It turns out the class of disjunctions in 2 dimensions are a rather simple class, and that's why I'm going to give that. So the concept class and the concept class is disjunctions in 2 dimensions. Plot these points. I can say in 2 dimensions I have a 0, 0, 0, 1, 1, 0, and a 1, 1. Right? Now let's think about all the disjunctions that we can have. We can have, let's call this x1 and this dimension x2. I can have x1 is a disjunction, x2 is a disjunction, x1 or x2 is a disjunction. I'm going to ignore this trivial case where nothing, right? First of all, what's r? Square root of 2. Why? Because you need a circle that basically you want the farthest point from the origin. So r is root 2, and that's not a that's a rather simple thing. So we're going to let that slide. In fact, I'll just put it in a corner in a different color. Okay. Now what's gamma? And that's where the question becomes tricky. In order for you to pick, even know what a gamma is, you need to know the function. Right? So let's consider maybe 1 or 2 cases. Let's say the true function, I'm going to call it f of x1 and x2 is equal to just x1.
These are simple disjunctions.
These are monotone disjunctions. Yeah, sure, yes. Yes. So consider suppose you have f of x1, x2 is just x1. In this case, the Novikov's theorem, what is the definition of gamma? Gamma is defined as the margin, right? Can someone tell me what's the definition of the margin?
The distance between a point.
The biggest or the smallest?
The smallest distance between a point and
any line that perfectly classifies. In fact, in the theorem, if you remember, it's not just any line, it's a line with a unit, a weight vector with unit norm.
Oh, okay.
But it doesn't matter. That was needed for the rest of the theorem. So, is the minimum over minimum distance between true classifier and any point. Right? So, this is the intuitive definition. I can write a more formal definition that gamma is a number such that y w transpose x yi w transpose xi is greater than or equal to gamma. It's some number. So I can pick a gamma here. So for x, this function, I can draw this line here that says positive on everything this side and negative this side. And gamma would be this gap here, this gap here, right? But that's not a good gamma because I can always move it a little bit this way and get a bigger gamma. But I can't move it a lot because if I move it here, then I need to consider this gap. So ideally, the line that gives you the maximum gamma would be exactly in the middle. So let's consider that line, and this gap here, that's equal. So really, what is the maximum margin here? What's the 1/2? 1/2. So gamma is 1/2. So now I can apply Novikov's theorem. So I have r square divided by gamma square. So this is root of 2 square divided by half square for this function, right? So that is for this function. But if I want to think about all possible functions of this kind, yes?
Sorry, this is for disjunctions?
This is for this disjunction.
Oh, got it, okay.
But if I want to think about the class of all possible disjunctions, I have to consider the worst case. The worst case, it turns out, is actually not this disjunction. It is x1 or x2, which assigns a plus here, a plus here, a plus here, and a minus here. Now, a line that separates these two goes in between, and what would be the maximum margin here? So can one person say the answer loudly and clearly?
Root 2 over 4.
Root 2 over 4. And there are many ways of getting this. My preferred way of thinking about this has to bisect these 2 points. It has to bisect this line here. I know the gap between 0, 0 and 1, 1 is root 2, and that means this is 1/4 of the distance. And at this point I'm just eyeballing it and coming up with the answer, and it's correct. And you can prove it if you want, using calculus and all that. But this should be so simple that it should not require calculus. But this is the quantity that gives you a bigger margin. So let's, original one was gamma 1, let's call it now gamma 2 is for this one. For gamma 1 we had root 2 divided by half square. For gamma 2 we have root 2 divided by square. This quantity is bigger, so that's the... So in general, when I give you a class of functions and ask you to think about them, think about the worst possible class of functions. Remember that the mistake bound is a worst case definition in terms of over functions. Not just functions but also sequences of examples, but when I give you a class of examples, you have to think of the worst class, worst representative.
Could you also mention what the unit vector is that's mentioned in Occam's theorem in each of these situations?
Oh, the unit vector is, so this is a line, right?
Yes.
I can, so can I erase this stuff, by the way?
Yeah.
Shall I erase?
So the answer is 2 to the power 4, right?
Yeah. Yes.
So for n equal to 2, the answer is n to the power 4.
The answer.
This particular.
Yeah, that's right. This is the thing, and you can simplify this so you get 4 power 2, which is 2 power 4. Sure. It just so happens that it's correct, the same. It's 4 power 2.
That wasn't one of the, in the quiz, that wasn't an option. N to the power 4.
N to the power 4 was not an option?
Because
The question probably did not ask for the margin, for the mistake part.
What was the maximum number of mistakes you can make?
It was in the form of 2 to the n and k, or 2 to the n.
Okay, let me take a look. I actually looked at that question a few times, and I think we got all the options right. Maybe there's some error. I think one of my TAs can correct me if I'm wrong. I think one of the answers is correct. One of the answers is correct, because I know that I worked through that a few times. Alright, so the second question that came up was, what is the unit vector here? And the unit vector is simply the, this particular line that separates out this thing. I can write the equation of the line, I can scale it up arbitrarily.
So you're taking a unit vector in the direction of that line.
It's the unit vector, unit normal, it's the unit normal vector to this line.
Oh, the unit normal vector to the line. Okay, that makes perfect sense.
Yeah.
Thank you.
Yeah. Yes.
I have trouble to construct a sequence to force the spectrum to make
Okay.
exactly 16 mistakes.
So the question was, and I think you had the same question in the last lecture, at the end of the last lecture. The question that, one of the exercise questions was, construct a sequence of examples that forces the perceptron to make these many mistakes. Right? I think that was for K disjunctions, if I remember right.
It's similar.
Right. So I have to confess here that that question is not as simple as it sounds. There was a paper on it. I can point you to the paper from '97 by Manfred Warmuth and Kevin and colleagues. Essentially the trick here, I'll give you the trick. I'm not going to give you the answer. And if you want, we can discuss the answer later on, because this might You know how in textbooks you have exercises at the back and there are stars next to questions? This is one of those questions with a star. Let's say you have a k disjunction. Without loss of generality, let's say the first k are present. So x1 or x2 or xk. And then there are also n minus k variables that are not in the disjunction. The way to think about this is the adversary, I'll give you the sequence of examples, okay? And then you can prove to yourself that there's an error or not. To make life simple, let's say that the bias is never updated, just to make things simple for now. First, I said x1 equals 0. So you start off with w equals 0. You set x1 equals 0, and I'm going to call all of these things that are not in the disjunction, I'm going to call that x bar. Okay? And x bar is 1, 1, 1, 1, 1, all ones. First example. This next example is x1 equals 1 and x bar equals all ones. Then the next example is x1 equals 0 and x bar equals, and then x1 equals 1. I'll do this, how many times? I'll do this n minus k plus 1 times, actually 2. I'll do this these many times. I am going to argue, and you have to prove a little statement at the end of this, that after this point, the weight w1 after this will become actually n minus k. And then w2 to wn will all be 0. Essentially, after this point, w1 would have been learned. Then you do the same thing for x2. x2 equals 0 and then x bar is all ones, x2 equals 1 and then x bar equals all ones, and so on. And then you do that n minus k plus 1, twice n minus k plus 1 times. And then you do that for x3 and x4. So totally, the total number of examples will be 2k times n minus k. So notice that I'm not really giving you how I get to the answer. It turns out this will work. I want you to think about it. This is not the kind of question that will show up in the exam. This is the kind of question that I might feel particularly nasty about and give it to you as a homework question, but not in an exam. But it is actually an interesting exercise trying to come up with this sequence, as I'm sure you've tried. Think of the sequence, step through the sequence. What will happen is every one of these examples will force a mistake, it turns out. First, the predicted label will be minus. The predicted label will be plus because the sign of 0 is plus and the true label is minus, so you will make a correction. This example will force a label minus, but the true label is plus. It will force a correction, and so on. And I assure you things will work out.
But then if n is k, then it's still O(n), not O.
K disjunctions. The usual assumption is k is a much smaller number than n in this case. And there are variants of this. This is just one of those sequences. There are variants of this. We can take that conversation offline. So it turns out that we are out of time. I bet many of you had other questions about homeworks and exams and such things. I think, did you have a question and you never got a chance?
Yeah, I never got a chance. So,
if it's 1 minute, I can take it.
Okay, this might be a stupid question, but last time we proved that a certain set of disjunctions are pack learnable, if I'm not mistaken. Will we be expected to perform a proof like that for another set of functions on the exam?
No, you won't, simply not for another set for sure, because essentially that process of proof is replaced by the Occam's razor theorem. So since Occam's razor is not covered, you won't have to do that. Alright, let's stop now. Anyone who came late, just a quick reminder, there is a midterm exam in the next class. I hope to see you all bright and early. And there's some event with pizza today. Check out the data club. Oh, also I have office hours right now if you're interested. that's actually what I was talking about at the end of the thing. So there are two ways of thinking.